Thanks for the kind introduction, and I also appreciate the opportunity to talk with our colleagues and introduce you some of the recent work my group have been working on in the recent couple of years. We are looking at the signatures from the power grid and looking at using them to answer some of the forensic questions about our multimedia information. Several of you were in the talk I gave last fall, which is on a broader scale to talk about the various aspects of multimedia information forensics, to look at how we can provide evidence and trace those evidence to make sure our multimedia information is used by authorized users for authorized purposes, and when there are things going wrong, we could collect evidence to figure out what has happened. So here I will do a little bit recap of some of the questions we raised from there, and then zoom in to talk about specific problems that I only very briefly skimmed through last time. So here we are looking at really as a role play, think of ourselves as Sherlock Holmes in the modern digital era, and looking at three major problems. The first problem we are looking at is about information leak. They are classified documents being in Washington, D.C. and surrounding area. We are not unfamiliar with any of the information leak. If there is an authorized group of users receiving this document, someone leak to the public, to the Washington Post, how could we know who was the source of leak and how can we discourage this leak in the first place? The technology behind it is to embed a tracer that we can identify individual copies, and that tracer is unique with individual ones. But we also want that tracer to be invisible to our eyes or inaudible to our ears if we have a sound signal. And so the basic idea, we embed something using what we call the spectral embedding. So basically we embed noise as our tracer, but each of the specific noise pattern traced to a particular user. The research issue around is how do we design that tracer? How do we embed it in an imperceptible way, as well as be able to reliably detect them? And we can also, how do we trace to the guilty person without falsely accuse the innocent? The next question we are looking at is when we do not have this kind of proactive embedding to embed the tracing, what kind of information we can gather. The question we raise here, considering a technology intelligence, a business intelligence problem, we have a picture here showing up on the internet and claim to be the next generation of X phone prototype. You can figure out what X is in this case. Now, from the competitor point of view, they want to know, hey, this picture looks real. Is it a real picture of an actual prototype, or is it a graphical rendering? So how can we differentiate a real photograph versus a photographical, a graphic rendition that looks real? And from the company point of view, if this is indeed a leak of their prototype, they want to know which employee in their company using their camera phone took the picture. So how can we trace to individual cameras, individual phones? So the idea behind answering this question is we look at our information processing pipeline. They are devices, they are sensors, they are processing modules and systems. Those sensors and processing modules can leave some invisible but detectable traces in the form of pixels. Among them, there's a specific relations when we pass through Canon's camera versus Sony's camera. And there are also sensors that has individual variations between them that will allow me to differentiate my phone versus Riza's phone. So that is the basic idea. We model this using signal processing and combine it with machine learning and also take advantage of some of the communication and other processing theories and the techniques. So we can answer those questions to trace to the individual users and to answer what kind of processing this picture has undergone, therefore tracing back to the acquisition devices and processing system. But there are two questions very difficult to answer. That is when and where. Think of we have a sound clip, someone is talking, and the content is very embarrassing or incriminating. If this is real as claimed, it was so-and-so said this on which day, where. And that can be a big deal. But how can we make sure that sound clip has not been tampered? And how can we verify this is indeed recorded at that day and at this place? So how can we answer when and where question? We don't have an embedded tracer. Even if we do, it's very hard. And many occasions we don't have the luxury to proactively doing that. And we don't have, even we analyze the processing system, we may not really know when and where. We could know what has been done, what processing and compression, what channel it has gone through, but we may not know when and where. And this when and where problem also apply not only to sound clip, but also to video, and for that matter, to any sensing sequences that is over time. So my favorite example to motivate this is using bin Laden's video. Many people around the world in terrorism want to know, given this video, when was it shot and where was it shot? Sometimes we could use a background if there's a landmark, but if it's an indoor scene or if it's a really too zoom-in view, we could not very easily using those kind of computer vision approaches. And there's also a soundtrack and a visual track. Are those soundtrack and visual track taken at the same time, or are they actually taken separately and then superimposed together afterward? So all these questions has great value in intelligence and also the authenticity and trustworthiness of some of these kind of documents. So these are very difficult to answer using the previous technology we developed and the community have seen. But in recent years, we have seen some breakthrough potentially could shine some lights to answering these questions. And that is looking at our environment. When we do the sensing, we are sensing devices in this environment. If it can pick up something in our environment that potentially could tell us only this specific time we have such signatures. And that is the focus of today's talk. And the signature we are looking at is from our power grid. That is the variation. What you are seeing is the variation of the frequency of this alternating current, and it's get induced and imposed into our recording naturally by many of today's devices. Okay, so what we are looking at, this is a slightly smaller view, is called the electrical network frequency, or ENF in short. This is basically the frequency of that alternating current of that powered our modern world. It's a 50 hertz in most part of Asia and Europe. And it's 60 hertz here in North America. Japan has both frequencies depending on where, which locations you are in that small country. But it's very interesting historically. Now this is what I call the nominal. That's we try to keep it stable in order for all the power equipment to many of the electronics working properly. But if we actually tap into our power network, just using a simple circuit, a transformer, and then we step down, divide the voltage to a safety range, and then we sample it into our computer to analyze. It's not exactly 50 or 60 hertz. It's actually very slightly around that nominal frequency. That is a result of a dynamic process between our ever-changing demand and our supply and the control mechanism try to keep up. So what we are seeing here is horizontal line is a frequency and the vertical is a time. So basically taking a very short samples, looking at a few seconds of our samples and then estimate the instantaneous frequency. And we do this for the next frame and so on and so forth. So we can see this is indeed around 50 hertz, but deviate up to about half hertz. Be assured this is not in US. Our US network is much more stable. It's at most about plus or minus 0.1 hertz, or oftentimes it's a much smaller variation. This was actually captured in India. Their network, their power resources are not as rich as ours, so you can see it's reflected into the bigger variation.
Color indicates amplitude over the spread of the spectrum.
The
color
is so this is like in the log domains.
So you are seeing signal over the whole range.
We are seeing the signal over a bigger range, but here we actually did some pre-processing just to zoom into the frequency ranges around 50 hertz. So we actually use a bandpass filter so to suppress the other frequency range, and we are going to see some more. Now, yes.
Fewer variations in the U.S. Does that make it harder?
They are depending on what questions we are going to answer. The dynamic range of variation is smaller, but it's still, we see that random variations. Now, if we have a very clean measurement from the power, and we are going to touch on the multimedia recording. If the multimedia recording, the ENF traces sometimes can be weaker. And that indeed a smaller dynamic range could make it harder. So I think it's really depending on situations. We are going to see actually there are bigger swings in a few slides. Okay, so let's see. This is supposed to showing up a video recording, video VNF. Let's see. No, but this is no. Let's restart that. Yeah, that's better. Now this is not a video, but they are rendering this spectrogram. So from a video sequence, if we analyze the spectrum over time, looking at the intensity of each frame and analyze how this vary, the average intensity vary over time, we could see a similar trends of variation concurrently taken with this power measurement. And this is random in nature, so we cannot really say what is the value in the next second, and so on and so forth. So the random process, that's nature, making this as a very interesting potential as a timestamp, because we could potentially tap into our power outlet, record this as our reference, and later on, if the timing information is under question, we would look at what ENF signals is in that recording and come to match at a different time of our references to see with which part we have the highest similarity, and that will be our estimated time, and also confirm the location. And you may note that this is a 10 hertz, not 50 hertz. I'm going to get to it. Okay, so this is what we are saying. So if we are aligning this at the proper capturing time, we are going to see a high correlation. And that would be indication that this will be most likely our capturing time. Okay, so the ENF traces have a few interesting properties. It is can be seen in many of the sensor multimedia recordings because of a few causes. Mainly, the power grid induces such traces in our recording. If we have if we connect it into the power outlet through the electrical interference. If the battery powered, depending on what kind of sensing mechanism we have, it could be coming from the electromagnetic interference. It could also coming from our power network drive all those lightings and electrical equipment surrounding us, and that could generate vibrations, acoustic vibrations or mechanical vibrations. And when we do the, say, sound recording, that could be captured. And we actually, if you listen closely in this room, we can also hear some electric hums. And for the video here, when we do the indoor recordings, our subjects, our scene is is powered by those lights, and those lights has invisible but detectable flickers. And I'm going to get more onto that. So there are various sources that are putting those ENF traces into our multimedia recording. Another very interesting property is if we're looking at the same grid, everywhere interconnected within this grid, if we're looking at the power ENF in our location in New York City, this variation, the main trends are the same. So we can pretty much, within a grid, just pick one location, record its references, and we will be able to determine or verify the time of recordings at other places within this grid. So ENF can be heard. This was actually one of the work got me interested in this topic. The pioneering work was done by a forensic scientist in Romania, Katalin Gregus, in the middle of 2000s, and he was given recordings from the court and to verify whether this time is indeed true. And he discovered that there's such time-varying variations of electrical network frequencies, and he can also measure that in the sound recording and find that this interesting random process, we can use that as a timestamp. And also, if we're looking at those variations in the time domain, the phase discontinuities, if we chunk off a segment, or if we're adding a segment, that could create discontinuities in both the time domain and in these measured frequencies. And that can be an indication there's some tampering on the content. So when I first learned this work, the pioneering work from Gregus in the audio engineering community, I was very fascinated by that. And being a visual person, my immediate question is, the sound signal is quite intuitive. We have the microphone is an electronic device, and that could be undergone some interference because of power grid. And also our sampling frequency is very high. Our voice on the cell phone of telephone is 8 kilohertz sampling. That's much higher than the 50 and 60 hertz we are looking at. But for video, there are a lot of challenges. For video, typically our frame rate is 30 frames per second or even lower. And that is much below the nominal frequency of ENF. So we would be looking at some aliasing effect. And how can we take advantage of that as a research question? And where are the potential sources? In the outdoor, it may not easily see some of such interference, but I was looking at the lights. The lights we have experienced, especially in old days, there's flicker. So can those flicker be detectable? That's the first question we want to answer. And if yes, and how can we extract this reliably, and how can we make use of it to answer forensic question? So that is the question, can ENF be seen? To answer this question, I call it we need to do some sanity check. Video camera, we have this aliasing problem. Potentially the signal is weak. I don't know whether it can be captured by the CMOS or CCD sensors. So let's start with the most favorable conditions. We will use a very sensitive photodiodes and has very high temporal bandwidth over these temporal domains, and looking at whether we can capture this flicker and how strong that is. So we are looking at this in the most favorable situation. There's no aliasing at all. We can sample at higher than twice of this nominal frequency. And then we'll be looking at more challenging situation. So this is what we did. Being a person in the signal processing more, working in the algorithms, I don't even have a hardware lab. So we start with buying multimeters and found very, very basic electronic equipment. And we build a circuit. It looks like this. We have a high sensitive photodiodes, about $10. This not too expensive. And then this is very sensitive, even just small changes in the light intensity will reflect into the changes in the current, and then we have two levels of amplifiers to amplify into detectable ranges, and we were feeding it into our computer to sample and digitize. And concurrently, we have our power. We tap into our power outlet using a transformer to step down and further divide the voltage. So this will get in our power reference signal. Okay. And here is what we measure from our power mains. It's 60 hertz here in North America. If we're looking at the light intensity by our photodiodes, it's not a 60 hertz. Actually, sensitive enough, we can actually measure that variation. Even though we cannot see, our electronic devices are sensitive enough to see the same kind of a sinusoidal variation, but twice of the frequency.
Yeah, because there's a full wave rectifier in your fluorescent light system.
That's right, and also the light intensity is really kind of independent and not affected by the polarity, only mainly by the current, the strength of the current. So we are looking at.
It's a square, I guess.
Right, it's a square, so that's the power law. Exactly, right. So it's a power law, so that's why we have 120 hertz. And also, if we're looking at the spread of that variations, that power law also amplify that to a wider range that we will see in the spectrogram next.
What are the vertical units?
Actually, this I think we normalize it, because we have a step-down divider, so I didn't record the absolute measurement here, but what we are interested here is how fast is the frequency, so we just can normalize the dynamic range. Okay, so how do we estimate the frequency, instantaneous frequency of short segments? There are many approaches. The prior art from audio engineering community use quite rudimentary approaches to count how many zero crossings over a period of time, and you need a sufficiently long segment, and also may not work very well when you have distortions and strong noise. In our engineering community, spectrogram is a widely used approach. It's a non-parametric spectrum estimation. We don't pre-assume any models, and we can take a short time Fourier transform and looking at the square magnitude over each of these frames, and to estimate the instantaneous frequency, we can look at the frequency range that surround this nominal and looking at which point we have the maximum energy. That's a very simple approach, easy to implement, but it could be quite sensitive to outliers when we have a sudden surge in the energy. So a more reliable approach is we can take a weighted average along each of the slices to looking at what is the frequency centroid over this targeted frequency range we are looking at, and that's again robust to outliers, and we could also zoom into different frequencies to looking for the base frequency as well as harmonics, and we can also merging them, looking at the signal-to-noise ratios over different range to make a more reliable decision. A more sophisticated approach looking at statistical signal processing, because now we have a sinusoid possibly buried in noise, and maybe multiple sinusoid both at the base frequency and all the harmonics. We could model this random process and looking at some special properties, and the typical ones we're looking at is the musical aspirator that is basically looking at what is the autocorrelation functions and building a matrix and looking at the signal versus noise subspace and using those to estimate the frequency. And this is, we can also take advantage of some stochastic models to look at how the frequency change over time very slowly and doing the frequency tracking. So in our initial work, we use a simple weighted energy with some interpolations in frequency domain, and later on we have changed it to music and aspirate, especially when we need more accurate and more resilient frequency estimate. So here is a block diagram. As an overview, we have the light sensing circuit, and then we have signal processing mechanism, and this is we have tap into our power network and sample what is the power ENF. So here, if our originally we can sample at 1 kilo or even below it, depending on the sensing device, sampling device we have. and if necessary, we can further reduce the sampling rate to just above twice of the nominal, and then we zoom into this particular frequency range through a bandpass filter, and then do the spectrum analysis and frequency estimation. After we did for both signal lines, the photodiodes and from the power, we can correlate them to looking at the cross correlation and looking at which alignment we have the highest similarity. So here is the results. This is from the power, and we can see in the spectrogram when we zoom in, we couldn't really see very thin line, but if we looking for a weighted average, we can estimate that frequency centroid. And this is from the photodiode. The power law is twice of that frequency, and also the spread of this variation is twice as large. And if we using the frequency estimation to plot, the blue line is from the power, and the dashed red line are from our optical sensing. And we can also compare the alignment of the power versus the optical sensing using different frequency estimation approaches. If you look at the zero crossing, it's very noisy. At the right alignment, we have the highest value, but the side lobe is quite high because it's a very crude approach and very sensitive to noise. The maximum energy is better, and the weighted energy is more resilient and giving us a more reliable alignment. Okay, so that's kind of a proof of concept that ENF is there, is potentially detectable by our optical sensors. And now let's look at a real video camera to see if our CCD and CMOS camera sensors, whether they are sensitive enough to sense the ENF, and also we need to deal with the aliasing. Most of today's video camera will sense about 30 frames per second or below it. Today's digital camera also follow some of the traditions from the analog domain. When we try to squeeze our analog video into 6 megahertz bandwidth with both visual and audio, there's some compromise, and also determine what is the right frame rate to make sure we have this kind of audio-visual multiplexing, as well as free from obvious artifacts and interference. The sampling rate at the analog domain for our NTSC is 29.97 frames per second on average. And in the PAL, in Europe and China, they have a 24.97 frames per second. So roughly it's 25, but slightly below. At this frame rate, we are trying to sense a nominal frequency of 50 hertz when we do this experiment in Asia. So we have a significant aliasing. And here is our analog signal from the power, and we are highlighting the twice of that frequency that from the light intensity of our fluorescent lights. So this will be our base frequency of 100 hertz, 200 and 300 are the harmonics. Now when we do the digital sensing at this frequency, we will have an aliasing. So it's a periodically tiling with this multiple of this sampling rate. So over one period, so at this sampled version, we have a periodic spectrum. We just zoom into one period, and we will find that this plus and minus 100 hertz got alias to just above 10 hertz. So that's why we see the spectrogram before was at 10 hertz. The harmonics was getting alias to just below 10 hertz, and then the 300 hertz harmonics got very close to DC. So if we have about 29.97 frame rate video camera and capture video in India or China, this will be where we look for. The 10 hertz range will be where we look for the ENF. And I'm going to get to if we have a 60 hertz, then our 120 hertz base frequency is going to be very close to DC. And that will be much more challenging to detect if we have a motion. So here we have done some experiment and done in India and China. They have 50 hertz power network, and we use different cameras to try, and also in US. So let's take a closer look at India. So this is from the power ENF, and this is from the video ENF. And we can see in that network, they have a very dominating base frequency. They don't have much of the harmonics, but the variation is big. Can be, in this case, about almost half hertz. And for simplicity, we started with a static video. There's not much motion. And if there's a motion, we need to specially handle it, because when we look at the average intensity of corresponding pixels over time, motion can generate some variation and contribute to very low frequency. And that could mess up with our ENF detection. And that therefore we need some special technique from image processing computer vision to handle motion. And so this is an example when we do a panning. So this part of the video scene is almost stationary, and this beginning part we are panning, so there are some camera motions. And you can see the ENF traces become much weaker. But with explicit motion handling, we can handle those. And overall, we still have a strong enough ENF traces for this clip to align with our power reference. And you can see the high similarity at this, I think both of the recordings started at the same time, so they align well at the 0 time lag. In US, it's more challenging if we have a more static video, such as a surveillance scene. Most of the time we have a still scenery. You can see this is aliased to very close to DC. But still potentially detectable. The signal-to-noise ratio becoming weaker compared with the previous case we have seen in India. And this alignment gave us about 32 seconds with 8-second time frame in our resolution. The actual delay we started this is 35 seconds. So we can control the frame size to balance and trade off the time resolution and the reliability in estimating the frequency, the instantaneous frequency. Now with this ENF serving as a timestamp when we align with the power references, we can use this for a variety of ways. And what we are seeing here on this slide is this is the ENF from our original recording. And if we take this video, insert a clip from another video, and then we're looking at the ENF extracted from this tempered version, we will see it varying here and then jump up to a high ones because that's coming from a different time, and the ENF is deviated from the nominal by a significant amount from that particular time period. So this, and when we finish up, it's dropped down to continue. So from this discontinuity, even if I don't have the concurrent power reference, from this discontinuity, we'll be able to have a smoking gun. There's something wrong with this video clip. It may be coming from a different source. If we have a concurrent references, we can pinpoint from which time and which grid this clip may be coming from. So that is for tampering detection. Another interesting use is for forensic binding. Looking at a video, we have the sound track, we have the visual track. From visual track, we estimate the ENF with this explicit handling of aliasing. From the sound track, it's much easier because our sampling frequency is higher. We actually have a little bit too many data, so we usually will use anti-aliasing filter to reduce the bandwidth, to zoom in to a much smaller bandwidth of our interest and extract the ENF from there. And then if we compare, if this sound track and visual track are captured exactly at the same time, they are influenced by the same power grid variation, they should share the similarity at the 0 time lag alignment. If not, then this is an indication that the sound track and the visual track are taken at different time. So the integrity, the trustworthiness can be seriously questioned depending on our application. Other research question is if we have very noisy sound signals, how can we reliably extract ENF? And some similar questions can apply to video as well. And another question is we are doing forensics. Forensics is not just have good guys gathering this evidence. We may potentially have an adversary who want to circumvent our detection and verification of time and place. Can they remove the ENF? The answer is yes. This is actually very easy because we are dealing with a very, very narrow band signal. Using a notch filter, we can remove this very well. But more realistically, many of the adversary may want to remove the original ENF and then superimpose another ENF from a time of their choice. So how can they forge this ENF without being detected? And we are looking at this from, we call this as anti-forensic adversary can try to fight against our forensic technology, and how can we counter that anti-forensic attacks? So we are looking at this is, our answer is it's easy to remove, but if we want to make a forgery of a valid ENF without leaving other traces, it's much harder. So we have some work published in the security conference of ACM looking at these anti-forensic and countermeasures. We were also looking at some additional application later in the talk. Okay, so far we have seen the basic extraction of ENF from our sound signal, from our visual signal, and compare with the ENF we obtain from our power references. And we can use this as a time stamping. And then the time stamping also giving us a capability to detect potential tampering if we see discontinuity, and also to bind the different sequences together. Now, from when to where, I haven't answered, can we verify the location? The location questions is actually quite interesting. What we have seen so far will be able to help us localize to an area. That is because the variations is tied with a power grid. If we have a distinct grid, in US we have 3 major grid systems. The US East, we have a very big areas, and the US West. And guess what? Texas is always special. So all those grids are not interconnected in terms of this frequency variation and the control. So if we're looking at the ENF signals at a given time, they will be independent changing. So what we can do is we can tap in 3 locations, one each in those candidate grid, and we recorded the references. Now when we have a piece of recording we want to verify, we can align with each of these references to see with which one at which time instance we have the highest match and above some threshold. And that will tell us the time and the location.
So presumably Alaska and Hawaii are part of your list?
Part of the, yeah, that's right. So they are independent unless we have paved a very expensive undersea cables to connect them. But that they are.
Historical records, they keep track of the frequency response?
Yeah, actually, so first, this is a very easy to record. It can be our DIY project. And second, in the power engineering community, they have been tracking this, not initially for the forensic purposes, but for monitoring the stability of a power grid. So they have some record, except the because of that motivation is different from forensics. They were using some phaser approach to focus on the power. So very clean, think of this as a very clean 60 or 50 hertz sinusoids. And they are estimating and tracking that frequency. So that resolution and quality may not be always sufficient to answer all the forensic questions. And I'm going to get into it. For answering the major trend, that's pretty good. That's sufficient. So there is a record. And with this coming, Europe is recording that, and I was told NIST is recording that, and the power group in Virginia Tech, in Tennessee, and also there's a forensic center in Colorado now also record that continuously. Okay, so we can track down. So if you have a piece of recording, we can tell what is the U.S. Eastern grid, or which of the potential grid. As long as we have those concurrent references, then we would just do an exhaustive search. Exhaustive search not just for the grid, also for all the possible time alignment. So that can be, if we are really searching in wild, that can be a lot of computation, nearly impossible, given the potential time we have, candidate time we have. So this prompts us two questions. One, if we don't have the concurrent power references, or if it's too expensive to run all the possibilities, can we, by just looking at the way it varies, some of the attribute of this ENF, can we first narrow down what is the potential grid it coming from? And then we look for some of the references and pinpoint time if possible. So how can we determine the location when we don't have this concurrent reference to do the alignment? And this flavor is a machine learning flavor. Can we looking at some particular characteristics? So here is what I promised. I visualized for you some clips of the ENF from the power network of US Eastern grid, and you can see, so we are actually aligned this as pretty much very similar scale. US is very, very clean. And to answer Aman's question, this is a variation is very, very small. But if we have a power very clean, this alignment should not be a problem. But if our sound signal is not very clean, estimated, a lot of distortion, that could be a problem. Now, India give us much bigger variations because of the control technology as not as sophisticated as us, and also their power resources. We need to have sufficient power supplies at our disposal in order to stabilize your system in view of a high demand. This, my student who also working on this, Adi Haji Ahmad, he was initially from Lebanon. And depending on the time and depending on the conflict that the area is in, the power can be very unstable and can really swing more than a hertz. And power outage is also quite common. So by visual examination, it seems to us there are some unique characteristics. Number one, by just looking at what is the average, we will be able to narrow down what is belonging to the 60 hertz area or 50 hertz area. But further looking at some variation characteristics, we will be able to potentially get some features and learn from those features to make an informed guess. So that is motivating a machine learning framework. The question is, what kind of features can we measure from this power grid, as well as from this piece of recording under question, and how effective that is. So a few attributes that we would learn. Mean values will quickly narrow down what group we belong to, the variance and the typical dynamic range. We are also looking at some statistical variation properties, so that motivates us to looking at some wavelet features. We are looking at the smoothened versions as well as a different level of details, and looking at the variance of those subband signals as part of our features. We have also done some statistical modelings of this ENF and find that they are very well fitting into AR process, autoregressive process of second order. What this means is, if I know the values, previous two values, I can predict next value very well, except up to some new information coming in. That's our innovation sequences. So using those modeling, we can take the parameters and the variance of this innovation as our potential feature as well. So we take these features and we can fitting it into a machine learning mechanism. Any standard would work reasonably well. What we use is the support vector machine, so that has very good generalization capability. And here I visualize for you different features, and you can see from the Quebec and the US East and the West, for some of the features can be very well differentiated. And in the 50 hertz range, we have China. So Lebanon is really a group on its own. And India and Ireland being a smaller grid, there's also a higher variation in general compared with a bigger grid. So using those visualization, we can see there are some potential separation capabilities using these features, and then the machine learning mechanism will help us finish the job. So that is the basic idea, that we are looking at just by looking at the characteristics of the ENF, try to learn the characteristics, and therefore when we have a piece of recording under questions, we'll be able to use machine learning to answer what is the likely grid it's coming from. Another intriguing question we want to answer is toward within the same grid. So in the power community, they are known that this ENF, because of interconnecting nature, so what we are visualizing are the different capacity power lines interconnecting our eastern grid. So anywhere the major trends, because that interconnection and also very fast response of the control, and the power is really transmitted near the light of speed, so very fast transmissions. So all those leading to the same grid, different locations share the similar trends of variation. And the intriguing question I was wondering is, could we ever use ENF to differentiate different locations within the same grid? So can we tell apart this recording is made in DC, not in New York City? Our intuition is if the fridge in my house got turned on, my light flicker. It would not affect results. So there are some kind of local phenomena that we could potentially take advantage, and there's something maybe unique to a particular location. So this motivates us looking at whether there's those kind of subtle traces among the shared trends that we could take advantage of and try to pinpoint the location using ENF traces. This has never been done. We get kind of giving it a try and also kind of try to face the challenges, and the challenges make us exciting. So this is what we did. We are looking at the microscopic traces in the ENF, and what we did is I solicited my past and former student and my student who are taking internship in other locations doing some multi-location recording. The first piece of recordings, simultaneous recording we did was a 3-location try. College Park here, Princeton, New Jersey, and Cambridge, Boston, Massachusetts. And you can see Princeton is almost in the midpoint. It's a little closer to College Park than Boston. So we did concurrent recordings, and each location, so we did 2 recordings. So if we correlate the recording 1 and recording 2 in the same location, they should have the best match. And this is the ENF traces. When we align and the main trend is the same, so we can use that property to align them well. And you can, if you zoom in, that's minor differences. And this is from power, so very clean. So we start with the most favorable situations to look at whether there is any differentiating factors at the location. Because those are very detailed. So if I just looking at the major trend, they are going to correlate very well, close to 1 in terms of the normalized correlation. So to amplifying those details, we are running a high-pass filtering to allow us to looking at how they differ. And then using those process version, we will looking at the pairwise correlation and visualize for you this is a segment of different recordings when we do the correlations. And this is the correlation coefficient. So here, the top line is I just use the 2 recordings in the same location. They are really close to 1 in the similarity. Most interesting one is when we correlate with 2 different locations. The black ones are when we correlate the Maryland, College Park, Maryland, and Princeton, New Jersey. They are the highest among all the pairs from different locations. And the green ones are Princeton correlated with Massachusetts. So they are very similar, but still lower. The distance is a little higher. And the lowest similarity is the detailed trends between College Park and Boston. They are the farthest apart. So what we found was those microscopic traces can be an aggregate effect of those little local distortions that are affecting individual locations. So the farther they are apart, when we are looking at a particular time instance, their similarity is lower. And that's what we are able to really relate this ENF similarity in the detailed trends with distance. So by measuring the ENF similarity, we can do an estimate of the potential distance, and that is starting to be interesting. If we can have these anchor nodes at a few locations, and then record this ENF, and then any piece of the other recordings, we can looking at their similarities in the detailed variation trends, and we will be able to make an estimate of how far they are to our anchor points, and that's a flavor of triangulations to pinpoint the locations. That's kind of a very most of the optimistic cases, but when you have multimedia recordings, the ENF estimate is more challenging. It's not as clean. It can have a lot of distortion. We need longer frames in order to make a more reliable estimate, and that could smoothen in some of those tiny differences depending on the location, very specific traces. So that add additional challenges if we want to do this on the media recording. Right now we are trying to gather a more audio recording, sound recordings concurrently of multiple locations. And we have some promising leads, and we still need to gather more data in order to verify this can be done on the media recording as well. On the power recording side, we could potentially use this to build some protocols, to potentially having some protocols to verify locations, to be able to solve the problem that you are where you say you are. And there's not a very reliable crypto or other security technology be able to verify, validate the location so far, without other kind of technologies assisting. So very briefly, to looking ahead beyond this adversarial relations in the forensic task, we are looking at some other applications. Along with the two colleagues in iSchool, we are looking at a historical recording. There are many of the recordings in the 20th century, especially around the 60s, 50s, and 70s. There's a presidential tapes, and some of those are of historical importance. One of the tape that my iSchool colleague pointed me is during the Cuban Missile Crisis time, if we could determine what is the exact time that is so far still unknown to the historian, that can be of very significant impact in studying the history as well as other social science studies. And for those tapes, are analog tapes, and through magnetic recordings, that's actually pretty favorable from looking for ENF. Except those are analog tapes, we need to digitize them in order to analyze more efficiently. During the digitization, there's another round of potential interference. So we potentially are looking at the true ENF traces. And this is actually from the digitized version of one particular Kennedy White House recording during the Cuban Missile Crisis time. And you can see actually there are two stripes. And this part, when you hear the tape, is actually suddenly stop, and then stopping the digitization. So from this part, we actually can infer this particular traces a little bit more deviated from the nominal. We are actually looking at the fourth harmonics here of our 60 Hertz grid. This could be most likely coming from the original recording time, and then the other ones coming from the digitization time. And you can see that these separations tells us the recording speed of the tape and the digitization playback speed are not exactly same, and that actually making it separated So if we want to really make good use of this ENF, tell us what is in the environment that the tape was actually recorded, this is a very favorable thing. So we can tell the archivist that when you do this digital preservations, actually recording, doing the digitization playback, slightly slowing down is perhaps a better way to do if we want to preserve these ENF traces. But in other situations, when the speed match very well, it could be aligned very well with the nominal frequency. So we can have two ENF traces on top of each other. And that's difficult to separate. One way we can tell the archivist from our study is during the digitization, we should record the ENF in the digitization time. Having that information will help us separate the two ENF and will preserve the original recordings ENF. Those knowledges was not there for the archivists know, but this study can help them. And also we have some digitization versions of the Apollo missions. NASA is interested in studying the historical records of multiple channels during the mission time of Apollo moon landing missions. And we can also see there are multiple traces. There's also some sudden discontinuity that's coming from there's nothing interested in the recording during that mission time, so they actually stop just to save the tape. And so there's something that more information that we could learn from looking at this invisible part of the data. Another interesting thing is to looking at alignment of multiple videos. Today, with image processing tools, we have seen very commonly, we can take a multiple picture, stitching them together using image processing and computer vision. That's stitching a panorama. But you rarely see a tool to help you to stitch together multiple video. So we can all attend a sports game or a wedding ceremony or attend other important events, but we could potentially give you a multiple view of these events, but we really have that tool. Why? Because not only when we do the video, not only we need the visual part to align, we also need first to align them perfectly temporally. So the time alignment needs to be done first very well before we can utilize that visual alignment. Using the ENF, we can potentially align them and without having to require Reza and I all download the same app or running the same protocols or buying really expensive equipment. One of the challenges to deal with camera in today's camera more increasingly are CMOS sensors. They are cheaper, they are low power, they're getting very well, but they have employed a shutter called a rolling shutter. Instead of taking the whole picture 30 frames 30 times per second, they are actually doing line by line. So think of your 1/30th of a second of that frame. Not that the whole frame are captured. We are taking the first line, and then we are taking our time to read out. And during that time, we are getting our shutter to capture the second line, and so on and so forth. And this...
That's a return to the way video was done before.
In the transmission, the line by line, in the transmission.
When there were CRTs, it was display line.
That's right.
And
that's right.
Visible distortion.
That's right. So this visible distortion, this is a fast-moving car. When you have captured to this line, the car already moving toward the left-hand side. So that's actually considered bad, usually, because of those distortional artifacts for fast-moving scene and objects. But think of our aliasing problem. Before we were complaining about 30, we only have a 30 frame per second capturing that scene, and we want to estimate something up to 100, 120 hertz. But if we can take advantage of that line-by-line sampling, we potentially can have a much higher sampling rate than that frame rate. So we need to take advantage of that and also handling motion. And if we do that, we will be able to capture, I'm going to show you this video. The blue line is what we estimate the ENF from the video. The the red line is from the power. If we do not take advantage of rolling shutter, do not take advantage of, do not handling motion, we can hardly estimate anything of the ENF from this video. But with those, we were able to really match and do a very good estimate, and they match each other quite well. So let me show you this video, and you can see the very fast moving scene.
It's interesting to do this. Wouldn't it make sense to timestamp the video in some way? Instead of using ENF, to actually insert something that would...
You can. The problem is how to synchronize mine with yours.
Yeah, well, nowadays, in order for GPS to work,
You could use...
pretty accurate clocking.
Right, so in the outdoor situations, we could utilize a GPS, but many of the today's situations you may not. So this provides a complementary modalities to solve the problem. I'm not saying this is the only way, but this provides something to work with when the GPS was not turned on or was not reliable in certain situations, because that GPS tag can be easily changed. Okay. So with that, to explore more, I quoted one of Gregor's initial papers, and he actually have several ones with kind of just slightly different variation, and including some published in journal on the audio engineering community. And then we have also a bigger overview on different aspects of information forensic. One section is on this ENF, and some of our research paper published initially in the ACM conference, and then more recently more complete version in journals, and some of the recent work is in the IEEE conferences. So I will stop here. Thank you very much.